Hi, everybody. I hope everybody out there was able to enjoy their Wednesday evening. I got a lot of work done. I am now most of the way through the lab report for next week's lab for this class. Excuse me. Gotta drink more water. And that will be available next week. Lab number 3, what is lab number 3 that you guys did this week? I don't remember. I can look that up really quickly, though. Where is my... There it is. What did I have you do last week? Oh, molecular models and nomenclature. Okay. That lab is due tonight. So make sure that you turn that in by the deadline. And also don't forget that quiz number 5 is due. So both those things need to be done by tonight. We're going to continue our work on Chapter 6 today. It is likely that we will finish Chapter 6, which means that I will get the quiz up sometime soon. That'll be the next thing I work on. And then we'll just continue from there. So the quarter is quickly approaching the end of things. So we're almost 60% of the way done. So hang in there. All right. So let's go to the lecture preview. Actually, let's go to this slide right here. Tuesday, we left off with this problem. I got to get my calculator. Where did I put that? And just as a little review to make sure that we remember what we're doing, because we're going to do this again today. We're going to go over how to calculate these quantities for this sample of sugar. So I have about half a gram of sugar. And I want to know how many particles of table sugar are in the sample, how many moles of oxygen are in the sample, how many grams of carbon are in the sample, and how many particles of hydrogen are in the sample. I'm just going to draw a line here so that I don't accidentally write underneath the problem. All right, so the first problem that we have a mass of sugar. And for the first of these problems, we want to figure out how many particles of sugar there are. Which means that I need to turn this into something, and then turn that something into particles. And the unit that we're going to use to turn from mass to particles, hopefully you're all saying it, is moles. So I need to know this relationship, how many grams of sugar are there per mole, and then in a mole, how many particles are there. Now, sugar has that formula as written on the board there, C12H22O11. And what I'm going to do is I'm going to look up the molar mass because I don't want to sit here and calculate it and waste time. So I'm going to calculate it off of Wolfram Alpha. And I'm going to type in the wrong sugar because I have too many of these memorized. And I got 342.30 grams of sugar is equal to 1 mole of sugar. And then down here for my relationship between moles and particles, well, how many particles are in a mole of anything? That's that number that you've probably already memorized if you've done the practice problems. .022 times 10 to the 23. So now that we have our setup over there, we can now start the problem with the mass that we were given, which was this quantity. .522 grams of sugar. Let's do the dimensional analysis. We'll turn grams into moles. And those units will cancel out. And then we'll turn moles of sugar into particles of sugar. Now, in this case, it would actually be appropriate to call them molecules, but I'll just use the term particles for now. That's fine. Finally, we put in our numbers. This was 342.30. And this was 1 mole in 6.022 times 10 to the 23. And those cancel out. I forgot to do that. So we punch it all in the calculator. And the answer I got for the first one was 9.18 times 10 to the 20, yeah, particles of sugar. And again, you can call it molecules, that's fine. Hopefully everybody got that when they did this problem over the last few days. All right, let's do the next one. How many moles of oxygen are present? So we'll scroll down. We're going to do the same problem that we just did with the same mass of sugar. But now our target is to figure out how many moles of oxygen are in there. And so I'll start in the same spot. Oops, not A. I'll write the wrong letter. Apologies for that. So I'm going to turn that into moles, just like I did before. And now I need a relationship between the moles of sugar and the moles of oxygen. This relationship up here is the same as before. But this relationship down here requires us to look at the formula. And if you look up here... Oops, my arrow didn't quite fit on the screen there. If you look up there, it's directly above the arrow, but at the very top of the box. I can't actually draw on that box in this window. You can see the formula. How many oxygens are there per molecule? Because if I had a mole of those molecules, or a mole of sugar, how many moles of oxygen would be in that sample? Type your answer in the chat. Tell me how many moles of sugar there should be, based on what we see there. Any of the 7 of you that are out there. How many moles of oxygen in 1 mole of sugar? 11 is right. Very good. Because you got that number from the coefficients in the formula. There's an 11 in the oxygen, a 22 in the hydrogen, and a 12 in the carbon. So if we're using something else, we'd use one of those other numbers. But since we want oxygen, we take the number for oxygen. Let me get rid of this thing. Now that we have all those relationships, let's write out the problem again. And the first part is going to be the same every time, because we're always going to turn grams into moles. And now that we get to this point, we'll turn moles of sugar into moles of oxygen. And this number is still the same, because it's still sugar that we're using, 342.30 grams per mole. And then in 1 mole of sugar, there are 11 moles of oxygen. Oh, I didn't draw a line, did I? Whoops. There it is. I forgot. My apologies. Same setup as before, but the last unit, we're going to do moles to sugar, turning into moles of oxygen. My very professional stream here as I draw beneath a window that nobody can see. Alright, and when I did that, I got... Oops. I'm using the wrong end of the pen. 0.0168 moles of oxygen. Alright, that's problem number 2. I gotta scroll up and do problem number 3. And what I'm gonna do is... I gotta put the red line underneath this so you can see it. We're gonna take this tool, and I'm gonna go like... Oh, that's not what I'm gonna do. There we go. We're gonna just take all of this stuff and go... Goodbye. Alright, so for the third problem here, I want grams of carbon. So I have grams of sugar, or mass of sugar. I was writing mass before. Now I have grams. That's fine. And I want to figure out grams of carbon. Now for this problem, I still got to turn this into moles. And I know that I can turn moles of any part of the sugar from the moles of all the sugar present. So I could figure out the moles of carbon from this. And if I know the number of moles of carbon, I can figure out grams of carbon using the periodic table. So let me put those relationships in here. I'm going to squeeze them in red here. This is still the same as before. For this relationship right here, in 1 mole of sugar, there should be how many moles of carbon? And so we look at the formula just like before, and because there's a 12 in front of the carbon, we would say that there are 12 moles of carbon per mole of sugar. And then down here, in a mole of carbon, there are, and what's my periodic table say? 12.0 something something. 12.011. All right, now we can do the problem. Set up the units just like before. And then we'll turn moles of sugar into moles of carbon. And then we'll turn moles of carbon into grams of carbon. So these cancel out, these cancel out, these cancel out. And now I just got to put in the numbers again. And you punch it in your calculator and the math does itself. And that's what I got, 0.220. And then lastly, I gotta make sure I don't go off the screen again. Let's... No, I gotta do this. That's not what I want. That's what I want. Whoop. Oops. There went everything. Hold on. Let's just do that so I know where to write. So you can do... Oops. Dang it. Hold on. You just ignore this part. Same as before, except this time I want particles of hydrogen. So how many hydrogen atoms are in this sample? So we'll turn grams into moles. And I know that I can turn moles of sugar into moles of any part of it, which I'll do H. And if I know how many moles I have, I know how many particles are in there. Now I can write the relationships again, so Same number. For this one, in a mole of sugar, there are 22 moles of hydrogen. And then down here, in a mole of hydrogen, we'll get that number right out of your textbook, because it's moles to particles. That would be 6.022 times 10 to the 23 particles of hydrogen. So you can see that we're doing the same sorts of conversions over and over and over again. We're always doing grams to moles, moles to some other moles, and then moles to particles. Those are the three types of conversions that we'll do. You just got to know where to get the numbers from. If it's a molar mass off the periodic table, that goes with grams to moles. If it's Avogadro's number, you use that for moles to particles. And then when you go moles to moles, you use the formula. And we're going to be doing more of these today, too. So let's do this last problem. I'm writing in the dead zone. There we go. I should be canceling my units. I forgot to do that. And then finally, moles of H. Ran out of space. And there we go. So 342.30. 1 mole of sugar is 22 moles of hydrogen, and in 1 mole of sugar is Avogadro's number of particles. I need to make this screen bigger, but then the text appears on your screen smaller. And that's not exactly something that I want. Alright. It's a number of particles, so it should be a large number, and it is. 2.02 times 10 to the 22 particles, or atoms, of hydrogen. Alright, hopefully those answers are what you got when you did these practice problems on your own. I guess what I should say is hopefully you did these practice problems on your own, because we're going to be doing more of that today. Alright, so... Oh, and homework practice. Yeah, let me put that on the screen for you to write down, in case you didn't get it yesterday. 629 through 640. Alright, for today's lecture, we are going to balance chemical equations. And this is different than what you have done so far in this class, but it's not difficult, I'll say. So this is kind of a nice little reprieve. We're going to have a nice, easy first hour of the class. Because what we're going to do is we're going to do actual chemistry. Hooray! Now, in chemistry, we represent things in the form of either a sentence, which would be me saying something like this. There we go. Sodium and water react vigorously to form sodium hydroxide and hydrogen gas. That's a lot of information. And parsing that information when it's written in a sentence is a little bit difficult, because you got to think, oh, okay, what's sodium? Oh, what's water? What are each of these formulas? What states are they in? How many of them react with what? So it behooves us to organize this information in what's known as a chemical equation, and that would look something like this. You have seen chemical equations before, but you may not have realized like what all the parts of the chemical equation mean. So the purpose of this section of the lecture is to talk about the different components of our equation and what the symbols all mean. The first thing we're going to talk about is what does the arrow mean, and what does it mean to be on the left, and what does it mean to be on the right. In a reaction, when we put stuff in a container, it reacts. And when the reaction is done, we make stuff. The stuff on the left is what we react, so it's called a reactant. Reactants always go on the left of the equation when the arrow is pointing to the right. It's probably better to say that reactants go on the tail of the arrow, because later on we're going to put the arrow in multiple directions. But most chemical reactions are written in the forward direction only. So reactants will be on the left, which means that what we produce are the products, and those are on the right. So reactants on the left, products on the right. The next thing that we're going to talk about are these numbers. Or no, I'm sorry, not the numbers, the phases. The indicators that come after these substances are letters or codes that represent the phase of the compound. And these are phases that you're familiar with because it was literally the first thing we talked about in Chem 121. They are solid, liquid, and gas. But the AQ one might be new to you. AQ means aqueous, and what that stands for is that this substance is not NaOH molecules or an NaOH ionic compound or whatever floating around in a giant chunk, or even as individual NaOHs. Anything that's AQ is interacting with water in a special way. For an ionic compound such as sodium hydroxide, that means that this sodium hydroxide, oops, wrong pen, has divided into its ions. If we wanted to indicate that the ions didn't form, so like this stayed NaOH, it was just solid and it didn't split up, then what we would do is we would put this after it. So whenever you see AQ, you should look at that and think, oh, is that an ionic compound? Because if it is, it will dissociate into ions. If it's a covalent compound, it doesn't dissociate, such as like CO2, but it can still interact with water and be dissolved in it. So you'll see AQ quite a bit over the course of the quarter. We're actually going to do a lab that specifically has AQ in it. All right, the last thing we're going to do is talk about these numbers in the front. And you're going to notice that for this one right here, where my eraser icon is pointed, I'm not pointing at a number, I'm pointing at a blank space in front of the hydrogen. Anytime you see a blank space in front of a compound or element, that is represented by the number 1. So there is 1 H2. We don't write 1 in the front of a chemical equation. If it was 0, then we wouldn't write anything at all. So if you had 0 H2, you just cross it out. It'd be gone. So keep that in mind. Whenever you see a blank space, it's always 1. It's never 0. Any other number we have to indicate by writing the number. These numbers are used to do what's called balancing the equation. An equation represents how atoms and molecules rearrange themselves to form new products. But those products can only be formed from the pieces that are available. You can think of atoms as kind of like Legos. If you grab something that is made out of Legos and then you try and build something with it, you only get the pieces that are available, so you can't create new pieces out of nothing. If you have 4 yellow blocks and 2 red blocks, you can't just summon a blue block if that's all the stuff that's available. Likewise, in a chemical reaction, all of the pieces get used, so you can't have leftover atoms without writing them in the chemical equation. So everything that is written has to be involved somehow. You can't just delete stuff that you don't need. Oh, I have extra sodium. Goodbye. You can't do that. You have to use every piece that you are given. Our goal for this lecture is to learn how to balance these reactions. And it turns out that there's really not a great way to do these other than to just take a reaction, sit down, and then just start plugging in numbers and use some intuition to guide you. So I'm going to give you guidelines on how to do this, but there's really no algorithm like you should start here and then you must do this and then you must do that, because every reaction is different. All right. Now, this property that we just mentioned earlier, the conservation of mass, is an observation that we make for all chemical reactions. You cannot create or destroy matter. So whenever you do your reaction, make sure that the number of things that are going into the reaction is the same as the number coming out. That means that we're going to have to tally our reactants and products in a sort of inventory. That just involves us to do some counting, which we can do. We can count stuff. So let's do some examples here. And I think I have, that's just always make sure it's balanced. We're going to learn how to balance stuff right now. All right. Now, when you balance an equation, it's very important that anything that you have on the left ends up also on the right. If it doesn't start that way before you are balancing it, make a note of, oh, this is not balanced, so I need to tinker with this. And then what you do is you edit the coefficients. The coefficients are those numbers that go in the front of the molecule. You cannot change the formulas. So if I have CO2 and I need another oxygen, I cannot just change it to CO3. That's not the same reaction we were doing. What I can do is I can put 2 CO2, and then I get 2 extra oxygen. And if I only needed 1, then I need to balance my equation further. So let's look at an example here. And the way that the slides are going to be organized for this is going to be really sloppy. So I'm going to be tapping forward through a bunch of these. So what I'm going to do is whenever I see my reaction arrow, I'm just going to draw a big line down the middle to separate my reactants from the products. And then what I'm going to do is I'm going to write down every element that I find in my substances. So I have a C, I have an H, and I have an O. I'm going to write all those out. Over here, I should have the same 4, so I'm going to write those out as well. Now I got to do my counting. How many carbon are on the left side? Well, I got 1 here, and that looks like that's it. So I'm going to say there's 1 carbon. How many hydrogen are on the right side? So I got nothing. I got 4 and nothing. That makes 4. And then finally, how many oxygen are on the left side? 2. I'm going to do the same thing on the product side. 1 carbon, 2 hydrogen, and then how many oxygen do I have? Well, I have 2 right here, but then I have this one here. That's a total of 3. That's where people will get messed up, is if they try and count everything that is on one side, but they omit an atom because it was off somewhere else. All of your atoms do not have to end up in the same spot. Oh, excuse me. So when you are yawning, you should not try and lecture. When you are adding up your numbers, double check to make sure that you've got them all. Look at the entire equation on whatever side that you're operating on, and double check that you haven't miscounted. All right, so the next move that we want to make is we want to evaluate what we've got. Is the equation balanced? And you'd look at carbons. Okay, carbon on the left is 1 and on the right is 1, so that one's good. Hydrogen on the left is 4, but hydrogen on the right is 2. That one's no good. And then oxygen on the left is 2, but on the right is 3. So that one's no good. If any of them aren't any good, then you have to balance the equation and start adding in subscripts. So let me get rid of these things, and we'll do that. So what I have to do is I have to add a coefficient to each of these. So I'm going to put a blank in front of each of these substances. And we're going to fill in the blanks. We're going to put numbers somewhere. When you do this sort of operation, it is a good idea to consider what you need to change and where you should put those numbers to do that. For example, I don't need to change carbon. I have 1 on both sides. So in this spot and this spot, putting a number would wreck that, unless I put the same number. So me putting a 2 in front of CH4 will make things worse. I will not be balanced. In fact, I will be less balanced than before. That means that my starting move is probably going to be in front of the oxygen or in front of the water. And the reason I'm going to start with the water is the following. I know that I have 4 hydrogen and only 2 over here, but they come in 2s. So if I do this and put a 2 here, then my balanced equation on the right side changes the number of things that are in there. Did I change any carbon? No, it's still got 1. Did I change hydrogen? Yes, I did, because I had 2 before. Now I have 2 waters, which is a total of 4 hydrogen. You can see that that makes a match there. Finally, what happens to oxygen? Did it change? Well, I still have these 2 right here. And I have 1 times 2 over here, so this became 4 as well. Now I need to balance out oxygen. This carbon is still good. We'll put his check mark back. I have 2 on the left and 4 on the right, and they come in pairs on the left, so the next move must be to do this. And once everything gets a check mark, once everything is balanced, the reaction is complete, and this is what you would observe in nature. If I take 1 methane molecule and 2 oxygen molecules, I will make a CO2 molecule and 2 water molecules. So that's how you balance equations. That's the inventory way to do it. Now, when you do these types of reactions, it helps to consider what the fate of your atoms is. For example, all of my hydrogen has to end up here. That's its fate. It's going to end up in water. So I know that if I relate the number in front of water to the number in front of carbon, those 2 should multiply together so that I have the same number. And that's what happened here. I have 1 CH4, so I have 1 times 4, or 4 hydrogen. On the right, I have 2 water, and each one has H2 in it. 2 times 2 H2s, or 2 times H2 is just 4. So knowing where your atoms will go and how that's going to affect your numbers will give you the edge in doing this problems. Alright, so let me scroll past all this stuff because this is just what we did. Let's do another one. How would I balance this equation? So, actually, you know what I want to do? Well, no, let me do this one. I'll let you work on the examples, because there's like 5 or 6 of them later. So we'll do this together. I'm going to inventory both sides, so I have 1 nitrogen on the left and 3 oxygen on the right. I got 1 nitrogen on the left and 2 oxygen on the right. This one's done, but my oxygen isn't. What's my first move? And when you look at this, you should see, oh, there's only one place that would make sense to start. And that is over on the right with NO2. The reason being, if I put something here or here in front of NO or O2, then this number will go up, and this number will stay the same, meaning that I am getting further away from what I want my reaction to be balanced with. Oops, there we go. So, when you put your number into the NO2 spot, you might think, oh, wait a second, this isn't really going to help me because I get 2 oxygens at once and I'm going to ruin my nitrogen. And sometimes that will happen. In those events, you just got to put a number down and see what happens to explain it. So this nitrogen becomes 2, and this oxygen becomes 4, because I have 2 NO2s. And now we need to ask ourselves, where can I get 1 nitrogen and 1 oxygen? Because that would balance my equation. And it turns out, well, we already have that in here. We'll do this. Now we've balanced the equation, and we didn't even touch oxygen, the O2 in the reaction. And that's fine. Sometimes you just get left with a 1, and that's okay. All right, so there's my inventory going over what I just did. All right. There are some tricks for balancing these, and it is all about figuring out where stuff goes and where you want it to end up, and then devising a plan to get the numbers one at a time, more or less. Try not to solve two at a time because that's very difficult in some cases. All right. Here's my Here's my tricks and tips for you. If you see any polyatomic ions, you don't have to write them as individual atoms. For example, phosphate here. Phosphate's got P's and O's. So you could just put P down and then say, oh, I have 4 O's. But what might end up happening there is you might have more atoms and you'll assign them to the wrong structure or part of the Lewis structure or something like that. So my advice is to keep polyatomic ions grouped together. Polyatomic ions are very stable. They don't tend to fall apart anyway. The next thing that you want to do is look at the molecules that you're working with and decide which ones are worth changing first. Anything that is really complex, you may need to multiply by 2 or something like that, but it's very unlikely you're going to have to put a big number in front of that. If you balance the equation and then you find out that the only thing that isn't balanced is your big molecule, changing its coefficient will change a whole bunch of numbers, and that's no good. So start with the complex molecules, the ones that have all sorts of stuff in it, and then do the simplest ones, which are individual elements by themselves, or hydrogen, or water, or whatever. Do those last. Finally, if you have H's and O's, you should balance them last. I'm sitting here yawning. Goodness, I need to drink more water. Balance anything by itself last if you can. If you can't, that's okay. You can do it as you go. Finally, if you're doing this process and you just get numbers that keep increasing, and like you go back and forth and back and forth and back and forth, and the numbers just keep growing and growing and growing, and you're thinking to yourself, there's no way that this reaction needs 90 calciums and 1 H2. What the hell is going on here? And the answer generally to that is, oh, you made a math mistake. Start over. So if you start counting numbers and they just get bigger and bigger and bigger and bigger and bigger, and I mean like greater than 50 to 100, like that's just way too big. Start your counting over and try again. See if you can find your mistake. All right. There's my sample problems for you. What I want you to try and do is balance these 5 equations. And in about 5 or so minutes, I will check up on you. We'll go over the answers at that time. Good luck. We're all counting on you. How are we doing? I see some answers on the board there. Does everyone else need more time, or are we all set? What would you like me to do? I guess what I should also ask is, do you want me to go over each problem individually, or should I just write the answers in on the slide? What would you prefer? Oh, I'm clicking in the wrong spot here. Someone wants me to go over it, so let me do that. So we'll do this. Will this fit? Oh, there's more of them in there. Let me just do 2 at a time here. So I'll go over the first 2. And, oops, didn't mean to dot there. So let's see here. So iron and oxygen make rust. I'm going to skip the phases because we don't really care about the phases for this exercise. So those are our substances on both sides. I have 1 iron over here, and I got 2 oxygen. Over here I have 2 iron and 3 oxygen. Now, a good first move might be to do something like this, because that matches up those. But now when I try and figure out my oxygen, I'm going to be in a weird situation. Like, what number do I put here that will fix this? And so the answer is, well, if you're in this situation, let's look at where this ends up. It ends up over here, and they come in groups of 3. So, knowing that... There we go. Knowing this information, what should I put in this blank here? In front of this oxygen and in front of this guy. Because they got to match, right? No number I put here will ever make an odd number. But if I put something here, then maybe that will work out. So let's try it. I'm going to put a 2 here, which means that this changes. And now I immediately know I could just do that. And then the last move is to change this. Oh, I actually put it up there. And there you go. So again, there's no one right way to do this. It's going to involve some back and forth, no matter what you do. That's the first one. I'm going to scroll that off the screen, do the second one. Oops, I didn't scroll far enough. Oh, wrong color. So I got mercury oxide decomposes into mercury and oxygen. And so I got 1 and 1, and then 1 and 2. Now, the first thing that I have to do is I have to do this. There's just nothing I can do to get the oxygens on the left. And if I add on the right, I just get further away. So I have to do this, which messes up my mercury, but that's a quick fix, and I can do that. And so now it's balanced. All right, do we get the gist of it, do you think? I'm going to go back to this, and what I'll do is I'm going to write in the numbers real quick. So these are the answers. And I'm just doing this in my head really quickly. Oh, this one I got to think about. So 2, 3, 3, 4. What else do I got here? So this is a 2. This is a 3. This is a 1, and this is a 6. And then 2. And you can see as I go back and forth, I'm doing these examples like trying to do it in my head. Where does this go? Where does that go? Where does this go? So those are the answers that I got. And if there's one in particular that you want me to go over, we could do that before we take our break. Is there any specific reaction that you'd like to see how I got the answer for? Type it in the chat. Let me know. While you do that, I will pet a cat. Hi. Hi, you're a cat. I didn't mute my mic. Oops. It seems like, I guess we're good if nobody's got anything else to ask. So I'm going to put the title card up. If you have any questions during the break, you can type it in the chat, and then we'll go over them afterward. But let me do this. Where is my timer? Uh-oh, why are we dinging? Oh, hold on. I must have a window somewhere that's unhappy. Oh, goodness. Okay. Hold on just a second. Why isn't it working? There it is. Timer? Timer, okay. I don't know what was going on there. Anyway, I'll see you in 10 minutes. Oh, I was so close. One of these days, huh? All right. All right, so I didn't get any questions, so we're going to move on to the next section, which is doing what we did yesterday with what we learned today. Not yesterday, sorry, Tuesday. There was nothing yesterday. I don't want to scare you. So all of that stuff where we were using like coefficients to figure out moles and grams and stuff, what we did with the practice problem at the beginning, we can also do with balanced chemical equations. And this is going to be the last thing that we do today. So let's put all of the pieces together and do some problems with this new concept. So here's a sample reaction that I have written on the board. And you'll see that I have the one here. Oops, that's not what I meant for it to do. I didn't have the pen selected. You'll see that I have the one written here faintly in green, because normally you wouldn't write it, but I just want to remind you that there is a 1 there. And what this means is that for every molecule of N2 that I react with 3 molecules of H2, I could react 2 molecules of NH3. Or I could produce, I should say. Now, I could actually take this reaction and create statements like the following. Oops, my PowerPoint didn't actually come up, or Photoshop didn't come up. All right. For this reaction, I could make statements like the following. For every N2 I react, I need 3 H2. And so what that would mean is that for every N2 that I react, I need 3 H2. And since we like to work with moles, we could do it like this. So for this reaction, this relationship is correct. For every mole of N2 I need, I also need 3 moles of H2. So for instance, if I said, oh, okay, I have 5 moles of N2, how many moles of H2 would I need? You would then set up this relationship right here, just like any of our any of our dimensional analysis that we've done before. And then I would say, okay, for every mole of N2, I also need 3 moles of H2. And there you go. So we're going to start constructing relationships from the balanced chemical equation. And these coefficients come from the balanced equation. So let's do another one here. So let's suppose I wrote this sentence instead. So now I want to do it in a different color here. For every N2 I use, I make 2 ammonia. And so my equation for this would be 1 mole N2 makes 2 mole NH3. Now we're only ever going to consider 2 things at a time, because I'm only ever going to ask you for 2 quantities at a time. I'm going to give you the first one, and then you will have to calculate the second one. The third thing is assumed to be in excess. And I'll explain what that means in a second. But let's suppose I had, 2.24 moles of ammonia. And I asked you, how much nitrogen did you have to put in here? Well, you just do the same thing that we've been doing all along. Use our relationship. I know that I have 2 moles of ammonia per mole of nitrogen, and so this would become that. Now, for the substance that is not used, here I used nitrogen and then ammonia. But hydrogen is involved. If the substance is unlisted in the problem, then they are assumed to be what is known as excess. If something is in excess, it means it's abundant and you have all of it that you would need. So you won't run out and the reaction will stop. What will run out first will always be the substance that you are given. Now, I could ask you a question where I told you how much of both were involved, and you'd have to figure out which one is the one that runs out first. And that would just be whichever one makes the fewest amount of products. But I don't know if there are any examples of that in the textbook, and that is more time than I want to spend on this topic, so we're going to keep it a little more straightforward than that. And we'll just stick to, I'm going to give you a substance, you tell me the other substance I ask for, using these ratios that are constructed from the balanced chemical equation. All right, and so here are the equations that we have for this reaction. One of those I didn't write on the other slide because I just ran out of space. But you could compare any two things you want. What's important is that you have the balanced chemical equation available so that you can grab these numbers straight from it. I ran out of space there, but that's okay. All right. Any other steps that you do for your dimensional analysis are the same steps that you did at the start of the chapter. So you're going to do grams to moles, which is look it up on the periodic table and add all the atomic masses together. Or you're going to do particles to moles, which is just Avogadro's number. So let's do a few of these problems. Now, unfortunately, I don't think that my balanced equation is on this slide, so I had to write it again. So, oops, not in green, though. Let's do black here. So I have N2 plus 3H2 makes 2NH3. And we'll go over to this problem. And we'll do that. And we're going to do this just like the problems at the very start of today's lecture, the extra problems, that is. So, what quantity am I starting with? I am starting with a mass of nitrogen. And the problem asks me, how many grams of ammonia are made? Now, with those two quantities, what I'm going to do is I'm going to use the balanced chemical equation to help me. So if I know the moles of nitrogen, and I know the moles of ammonia, I could convert between them. Because I know that the ratio for moles of N2 to NH3 is just those balanced chemical equation coefficients. And that would be 1 mole N2 equals 2 moles NH3. And that comes straight from the balanced chemical equation, like we just did. Now I just have to get to these parts, and we have already done that before. You know how to turn things from grams to moles. So we got to go look this up. How many grams of N2 are in a mole of N2? This one I might know. I think it's 28. 28.02. Grams of N2 is a mole of N2. Make sure that when you're doing something like N2, you add both of the nitrogens together. And then for ammonia, that one I'm going to type in my calculator. It's 17 something. That is 17.03 grams of ammonia, 1 mole. All right, we got all the relationships written down. So let's start the problem with what my problem gave me, which is 5 grams of N2. I'll use my little map that I wrote out here to go from grams to moles. And those cancel out. Then I will go from moles of N2 to the next unit, which is moles of NH3. And then finally, I'll take my moles of NH3 and I'll turn them into grams of NH3. And then it's just a matter of filling in all the numbers with the relationships that you have written out. You punch it all in the calculator. And my calculator gave me the answer 6.08 grams of whatever this was, NH3. All right, there we go. Let's do another example. So I'm going to give you 2.75 grams of hydrogen to make ammonia, and I need to know how much nitrogen is also needed. So be careful, because there's only 2 of these substances that you want in this problem. So this is written here, the word ammonia is written here, and then you have this right here. I'm going to put the equation back up here because for some reason it keeps disappearing. So that is N2, 3H2 makes 2NH3. All right. And this problem is exactly the same as the problem that we just did. So what I want you to do is try to solve this problem. Plot out your little path by making your unit map. Enter in the relationships like I have been doing for you. And then do the calculation. And when you get your answer, type it in the chat. We'll go over the answer in about 5 or 6 minutes. All right, just a few more seconds to finish up. We'll go over the answer. All right. So let's do that. I probably should have left that on the screen, actually, because it's very similar, but that's okay. Okay, so the quantity that you are given to start is grams of hydrogen. And it asks you how much nitrogen is needed in grams. It doesn't ask you anything about ammonia other than just that you're going to use it to make ammonia. So we're not going to solve for ammonia. We're going to solve for N2. And we want to know its mass. So what that means is we're going to need to get moles of hydrogen and moles of N2 and relate them together. And if I can turn my grams into moles and my moles into grams, I'll have the solution. So let's start with the central relationship from the balanced chemical equation. Moles H2, moles N2. And according to our balanced chemical equation, for every 1 mole of N2 I need 3 moles of H2. And then up here, I can relate H2 in grams to moles. In 1 mole of H2, there are, I gotta type that in the calculator, 2.016 grams of hydrogen. That number got a little bit, oops. A little bit moved there, hold on. All right, and then down here, I have 1 mole of nitrogen. And that's still 28.02 grams of nitrogen. I think it's 2. Whatever, it's close enough. All right, so let's do our problem here. We got 2.75 grams of H2. I'm going to turn grams of H2 into moles of H2. We'll do moles of H2, moles N2. Just following my flow chart here. Getting tongue-tied on just random words here. I'll turn moles into grams of N2. And then we'll just run the numbers. So we'll just put in the numbers that we wrote from those relationships. This was 3 to 1. This was 28.02. Now when I punch it all in the calculator, That's what I get. 12.7 grams of nitrogen. Hopefully that is what you got too. My slide says 12.8. It's close enough for government work. And this is a union job. All right, let's do something different than ammonia. Let's do a different reaction here. So sodium azide is this substance right here, NaN3, and this is used in the airbags in your automobile. The way that this works is we have this powdery stuff, and we hook it up to a circuit, and the circuit is completed if something strikes your bumper. Like if the car detects a bumper, it pushes the bumper in, it starts a circuit, the circuit ignites the sodium azide, which produces nitrogen according to this reaction. And the nitrogen then goes up the steering column, fills the airbag, you presumably hit the airbag instead of the steering wheel, and it still hurts because it's an airbag. It's really fast, and you can break your arms if they're in the way. So don't drive at 10 and 2 like a granny, because the airbag will break your arms. So my question here is, what mass of sodium azide would have to decompose to create 253 million molecules of N2? Now, that's a big number, it looks like, but for this problem, it turns out that's rather tiny, because, as we'll see, we're going to get a very small number. So I'm going to do this problem with you, and then I believe we'll just get to the practice problems at this point. So let's do this. And then we're all done for the day. So I have no problem with doing more of these problems with you. All right. So my starting quantity this time is not a mass. It is a number of particles of N2, because I want to know how much of the other thing, which is the grams of NaN3. I didn't mean to have a little dash there. That I need. So just like before, I need to set up my mole-to-mole ratio, and I need to do it with these two things. So let me write those in the middle. Mole N2, mole NaN3. And we'll start by making this connection by using the balanced chemical equation, which didn't show up in my capture, because I didn't capture it. Let's do that. So I know that for however many moles of N2 I need, I will also need some number of moles of NaN3. And according to the balanced equation, the number that's in front of N2 is a 3, and the number that's in front of NaN3 is a 2. So that relation's taken care of. Now I have to do this one up here. How many particles are in a mole? You should already be writing that number down. And then finally, how many grams of NaN3 are in a mole? That I gotta look up. The number that I found online was, oops, wrong color. There you go, 65.01 grams NaN3, 1 mole NaN3. Oops, I ran out of space. We'll just do that. Oops. All right, it's there. You'll just have to believe me. All right, now we can set up the problem. So I have some number of particles, which is 253 million. I'm going to write that in scientific notation, just because that's how I'm going to type it in my calculator. And then we do the dimensional analysis, so I'll do particles N2, moles of N2. I'm going to run out of space, but that's okay. Moles of N2, moles NaN3. I should have canceled those earlier. I'm going to move this down here. And we'll cancel moles of NaN3 on the bottom. And grams of NaN3 on the top. All right, let's run the numbers. In a mole, there are Avogadro's number of particles. And then our ratio here was 3 moles N2, so I got to find the N2 and put the 3. 2 moles NaN3. And then finally, 65.01 grams per mole, based on what we wrote down before. Punch it in the calculator. What do you get? And you get the tiniest number. So the reason that I like to show this problem is that depending on the nature of the question I ask you, you may get really, really, really small numbers. And you should not be intimidated by the fact that you see an answer that looks outside of your comfort zone. Something times 10 to the minus 16 is beyond a pinprick of material. Oh, that's not the answer I got on the slide. Did I make a math mistake? Hold on. Let me go back to my work here. 2.53 times 10 to the 8 times 2. Oh, I didn't multiply by 65.01. That's what I didn't do. Okay. I missed this number down here because I didn't put it in the calculator. So let me erase what I put here. I didn't need to erase that 10. That was dumb. All right. Now my answer does match. 1.82 times 10 to the minus 14. But again, that is a very, very small mass. Like if you took a pin and poked like a crystal of sugar and tried to put that on a balance, that would be far more than 1.82 times 10 to the minus 14 grams. That'd be like 10 to the minus 6 grams. So you'd have to like cut a tiny, tiny crystal by a factor of like 1,000,000. So when you look at this problem and say, oh, that's so many molecules, remember that molecules are really small, and so they don't add up to very much mass. And that you need like 10 to the 23 molecules to get grams worth of stuff anyway. All right, so these are my last few problems that I have here for you. What I want you to do is to do this problem with this equation. Note that the equation is not balanced. You got to balance the equation first before you do anything, so do that first. And if you use 0.522 grams of KClO3 and decompose it, how much KCl is left in the tube? How much oxygen is available if you do the same experiment? And then finally, has the conservation of mass been verified? You're going to look at the numbers before and after that you get, and we'll compare them together. So I'm going to give you about 7 or 8 minutes to do this. We'll go over the answer. Then we'll be all done, because that's the end of Chapter 6, I believe. Yep, it is. There's my little work. So go ahead and work on these. I'll check back on you in a bit. Type something in the chat if you need help, because I will just be right here. And good luck. That was me just trying something. One of my windows closed. Okay, good. It popped up over there. I didn't know if I would have to refresh the window or not. How are we doing? Does anybody have any questions? Has anyone gotten the answer for how much KCl is left over? Type it in the chat when you do. All right, just a few more minutes to go over, finish the problems, and then we'll solve them on the board. All right, let's go over the answers. Oops, that's the wrong button. So first thing we got to do is we've got to balance the equation. Actually, that requires me to write on this screen. And so hopefully you balance the equation with these numbers. Otherwise, everything kind of falls apart from here if you didn't do this with the right numbers. So once we've done that, now I can go to this screen. And how much time do I have? I have 5 minutes, so I'm just going to show you the answers here. So 0.522 grams of KClO3. We're going to set up the unit conversion just like we did before. I just don't have time to draw out the little flow chart. Oh, shoot. Sorry, this is KClO3. This is KCl3, and then when we get to this point, it's KCl. Oops. That should be KCl, and then grams KCl. And then how many grams are there for KCl3? I gotta look these up. Where'd my Lentec go? There it is. KClO, oops, O3. That's 122.55. Per mole. KClO3 is 2. KCl is 2. And then KCl itself is 74.55 grams per mole. Didn't cancel those out. So I punch that all in the calculator and I get 122. I got 0.318 grams of KCl. Now I'm going to do the exact same equation, but I'm going to solve for oxygen's mass this time. What am I doing? Hold on. Sorry. Oh, I lost all of my... Where the heck did all the windows go? I did something to my thing here. Okay, I can't actually... I don't have, like, the pen available for some reason. So I can't change this unless I just close the program, and I can't do that. I hit a button and, like, it screwed up what I see. That should be a 3 there. Okay, so those cancel out. Those cancel out. There we go. And so this is the same as before. This one is a 2, but the oxygen is a 3. I can't actually see it because now I have a brush in the way. Yep, there we go. And then this one is 32.00 over 1. And when I do all that, I spit that out on my calculator and I get this. And then the last question that's asked is, was the conservation of mass verified? Well, if it was, then whatever matter I started with before, which was this, should be equal to the matter that I was left over afterwards. So if I add my two answers together, you get exactly 0.522. And so, conservation of mass was verified by this experiment. And in fact, all chemical reactions do obey the conservation of mass. All right, there's the homework practice for this section. that is the end of Chapter 6. When we come back on Chapter 7 for Tuesday, we're going to study the gas laws. We're going to do a little bit more math, and then we're going to talk about some states of matter. And we're going to start winding down the quarter from here, which means that when I go back to the title screen here, since that was the hardest part of the class that I think for 121, we get to go back to the daytime. We get to have the happy music playing again instead of the angry, awful music. I want to thank everybody for coming out tonight. Have a wonderful weekend. Make sure that you are studying, doing these practice problems. Finish all of the stuff that is due tonight. Quiz number 6 will be put up and will be due at some point next week. Have a wonderful weekend. Stay healthy, stay safe, and stay home.